Well, we're beginning Chapter 11, a short chapter that contains a lot of review material about intermolecular forces and the impact they can have on the state of matter that substances can assume. So this first part, I'll cover the first 12 slides of the PowerPoint. Clearly, I'm not going to go over the fundamental difference between solids, liquids, and gases. You know that we go from highly ordered solids with strong intermolecular forces of attraction to much more disordered gases with weaker. And it has to do either with the presence or absence or addition or subtraction of energy, like heat, for example. We call solid and liquid states, though, condensed phases because those particles are closer to each other. So that's something that's new and different. And the state of a substance is at a particular temperature and a particular pressure depends upon two things. It depends upon how much kinetic energy they have, and also what we're going to focus on now, the attractions between particles. So make sure you're familiar with the characteristic properties of some states of matter as are summarized in this chart below. So let's make sure we know the difference between inter and intramolecular. Inter means between two different molecules. So that would represent not a bond, but a force, a weak force of attraction between two separate molecules. Intramolecular forces are referring to the bond between two atoms within a molecule. Now, while these forces are weak, they are strong enough to be able to determine things like what temperature does a substance boil at, what's its vapor pressure, how easily it can flow if it is a liquid, etc. So the intermolecular forces as a group are called van der Waals forces, and I've heard sort of variations of that. But what we're going to start with, sadly, is the one that is in the intermediate strength category. If it were me, I'd go a little too big, but let's start with the dipole-dipole interactions. Then we'll look at dispersion forces. Then we'll examine the strongest of the weak intermolecular forces, hydrogen bonding. Now, one of the intermolecular forces that we did not study last year are ion-dipole. Anything that has a charge is attracted to something else that is oppositely charged. And we've talked about positive and negative ions and partial positive and negative molecules. But what's interesting is that you can have ions, as pictured here, with either a negative anion or a positive cation, also attracted to oppositely charged partial charges on dipoles nearby. So this dipole is a molecule that has kind of a positive end and kind of a negative end, either because of, mostly because of differences in electronegativity. The more electronegative element of the partnership hogs the electrons closer to its side, thereby making it more negative. That means if there was a positive sodium ion nearby, it would be attracted to the negative end of that dipole molecule. So that's a ion-dipole interaction. It explains how things like water can dissolve ions, a molecular substance dissolving an ionic solid, but it is between ions and polar molecules. Now there is another dipole-dipole interaction that we talk about when we have a pure substance that is made up of polar molecules. And as you can see, these molecules have permanent dipoles. They're not going to be temporary, as we'll learn in just a moment. And the opposite ends, for example, a negative end of one molecule would be attracted to the positive end of another. And you would have repulsive forces then between two like-minded charges. So two negative ends or two positive ends will have repulsive charges. So what happens when you have sort of a molecular soup of a dipole, a charged molecule, you have the alignment of the molecules in such a way that they try to minimize the repulsive forces and maximize the attractive forces. So dipole-dipole interactions are between two or more polar molecules. And the reason they are permanently polar is because they don't share their electrons equally between them. Now, the more polar a molecule is, the higher its boiling point. And I have no idea what this unit means. That's the debye, symbolized with that funny little dipole moment. That's the name of the unit, debye. And the bigger this number gets, basically what it means is that the stronger the dipole-dipole interaction is between two molecules. In this entire chapter, you will be able to evaluate the strength of intermolecular forces, not bonds, by their boiling point. As the dipole moment or Debye value gets larger, you can see that the boiling point gets higher and higher. As things hang on to each other more strongly, it takes more energy to break those intermolecular forces so that they can be free to go turn from a liquid into a gas. Please notice that they selected a bunch of polar molecules that are roughly about the same molecular weight, and I'll explain why that's important in just a moment. So that's a dipole-dipole interaction. Of the three that you're expected to know, it is intermediate in strength. Remember, ion-dipole is sort of a separate force. Now this next force, called the London force or London dispersion force, is the weakest of the three. And what can happen is that, for reasons that people don't really explain, suddenly either a molecule, or in this case an atom, can become polarized. They have polarizability. For reasons we don't really know, all of a sudden this electrons run to one side of the molecule or atom, making that side partially negative. That's what that symbol means. And temporarily, if this is the end of the atom or molecule where the electrons aren't, that's where it's kind of positive. So you get something that's called a temporary dipole. Now another name for this is temporary induced dipoles. These are not permanent dipoles that are always polar. They just suddenly change from being neutral into kind of a polar atom or polar molecule. Now the induced means that, let's say, as we look at these before and after pictures here, this is helium atom 1 and this is helium atom number 2. And if all of a sudden helium atom number 2's electrons run over here, then they're going to repel the electrons in another helium atom nearby and make them get pushed aside, leaving you with the formation of two temporary dipoles. The part of each of the atoms where the electrons are kind of negative, where they are not are kind of positive. And when the partially negative side of one atom or molecule is attracted to the partially positive of another atom or molecule, that's this dotted line. That is the location of the London dispersion force. It's temporary because it won't last. It's induced because one atom or molecule starts and then you get a chain reaction going within the container. And the third reason, induced means somebody made me do it. And the third term, dipole, means temporarily they make a little polar molecular atom and opposite ends attract. Very weak, but very important. Those are called dispersion forces. The instantaneous dipole was the one that started it. The induced dipole is the one that responded. In the next nanosecond, helium atom number 2 will go back to being normal again, but helium atom number 1 might make another atom next to it get induced into becoming a dipole. And it goes on and on and on and on. So every substance has dispersion forces. Keep that in mind when you answer any question. All substances, whether they're polar or nonpolar, have London dispersion forces. And the tendency of that cloud to be distorted and shift in one direction or another is called polarizability. Now, the factors that affect London forces are two things: the shape and the molar mass. So if you look at these two guys right here, these are what we learned in the last semester, isomers. This is N-pentane, 5 carbons with a bunch of hydrogens attached. This is neopentane, not in a chain anymore. These are kind of sausagey, these are spherical. So long, skinny molecules like the N-pentane have ability to have all between two molecules next to each other spots for London dispersion forces to take place. Whereas if you're spherical, you have less surface area and therefore theoretically weaker London forces, even though they're the same molar mass, because they have the same number of carbon and hydrogen atoms. Notice we can verify this with the boiling point. You should interpret higher boiling points as meaning stronger intermolecular forces of attraction. So surface area or shape is one factor. The second factor I think you can deduce if you just stare at this chart for a little bit. Here are the molar masses of, say, the halogens. And notice as we get heavier in the halogens or heavier in the noble gases, the boiling points are also increasing. So the reasoning behind this is that as you have an increased molar mass or molar weight or molecular weight, the assumption is you have a bigger electron cloud. And if you have a bigger polarizable electron cloud, that means the shift of the number of electrons is greater, the separation of the positive and negative charges is greater, and you're going to get a stronger, relatively speaking, temporary dipole. And therefore, the forces of London forces between those two temporary dipoles will be stronger and boiling points will be higher. So greater the number of electrons as a function of something's molar mass or molecular weight, the greater the strength of the London force. Now, if you have questions where you have to compare who's got a greater impact, dispersion forces or dipole-dipole interactions, if you have two molecules that are about the same size and the same shape, same mass, then the thing that's probably indicating a difference in their intermolecular forces is the strength of their dipole-dipole interaction. Remember, that's a permanent one, and it's a function of differences in electronegativity. The greater the difference, the stronger the dipole. If one molecule is much larger than another, then the dispersion forces are going to determine its physical properties. Let's go back to that slide previously so I can focus on it. Fluorine is a gas, so is chlorine. Bromine is the liquid, and iodine is a solid. And the reason why they become progressively more organized forms of matter going down the column is because since they have greater molar mass, they have stronger London forces, they have greater intermolecular forces that hold them together, and therefore their form of matter is more highly organized. So at room temperature, iodine is a solid, whereas bromine, a less organized form of matter with weaker London forces, will be a liquid. So it's very important London forces are on the form of matter that a substance will display. Okay, now this particular slide I will stop at and finish this first podcast because this is the introduction to hydrogen bonding, the third intermolecular force, even though they call it a bond, that we will be discussing next. Until next time.